This meeting is being recorded.
So yeah, our next speaker is Ansgar Graf, speaking from Paris, and we're glad to continue with London-Paris connection.
Thanks.
You're not sharing your screen currently.
What? But I shared it, no? So I lost it? Okay. I have to confirm that it's recorded. Okay. Well, why does it stop? It already worked. Okay, does it work now? Do you hear me? Hello? Hello? Can you hear me now?
Yes.
Okay, great.
You've lost the sharing.
But what? Why?
Go back to your slide.
Okay. Okay, so thanks, welcome everybody, and thanks for the opportunity to speak here. I'm a PhD student at LPS Orsay, and I would like to talk about a class of semimetals that I've been studying theoretically with my supervisor, Frédéric Pichon. I will start by a short introduction to topological semimetals and then tell you how they are linked to what we call multifold Hopf semimetals. I will describe some of their properties, and then in the end, I will explain you why this word Hopf why this word Hopf appears in the title of those semimetals. And this is due to a relation to Hopf insulators. So topological semimetals you can understand by a comparison to a simple semiconductor like gallium arsenide. If you go close to the Fermi level, you have these parabolic band edges, which are called Schrödinger fermions, and which are described by a single band effective mass Hamiltonian like this. And recently, people started to look at some different classes of materials which have these linear band crossings. Okay. Which have these linear band crossings close to the Fermi level. And those are called wild fermions, and they necessitate the description in terms of a 2x2 matrix Hamiltonian. This, like this, with Pauli matrices. And beyond wild fermions, there are other classes of topological semimetals, notably Dirac fermions, which have these two superimposed wild cones with gamma matrices, which are Dirac matrices. And recently, people have also studied so-called unconventional fermions, which are also called chiral multifold or pseudospin S fermions, which have 3, 4, or 6-fold crossings. And experimentally confirmed are already a certain number of those materials, which you can see in this table here. Now, where's the topology in those? This is linked to Berry monopoles. So to understand this, we have to look at the Berry curvature, which is an antisymmetric tensor in the space of the momentum coordinates. And in 3D, you can write it in the form of a pseudo vector, which is a 3-dimensional real vector. Now, for a wild fermion, which is just this crossing, you can compute the Berry curvature, which takes this form Q over Q3, which is a monopole form, and which is called a Berry monopole. And this monopole vector field is really located at this nodal point here. Now the topology is in the Chern number, which just measures the flux of this Berry curvature through a surface enclosing the nodal point. And for this wild fermion, it's just ±1 for the upper and lower bands. You can play the same game for these multifold fermions. For example, with this threefold spin-like crossing, you have Chern numbers -2, 0, 2, and with a fourfold crossing, you have those Chern numbers shown here. Importantly, they are distributed antisymmetrically with respect to zero energy, which means you have this Chern number sum rule, and you have a trivial flatband in the sense that the flatband carries no Berry curvature and no Chern number. And this will be important for comparison later on. Now, we cannot have a single monopole because for the Briançon to be periodic, there cannot be a flux through the Briançon boundary. So for every source of Berry curvature, you also need a sink. And I want you to view this as an extended Berry dipole, which is in the Briançon and which is separated by some distance or by some vector d0, which is like a dipole in this topological sense. This extended Berry dipole is responsible for non-trivial surface states of semimetals, such as the Fermi arcs. So here you have your source, and here your sink of Berry curvature, and every 2D slice in between them is like a Chern insulator with edge states, which taken together form this Fermi arc here. And you also have many other unique physical properties caused by this Berry dipole, such as anomalous Hall effect, negative magnetic resistance, Landau Hall effect, and peculiar Shubin of the Haas oscillations, which I will not talk about. What I want to talk about is the merging of monopoles. So if you merge two wire nodes, a minimal continuum model to do this is given by this Hamiltonian. So we merge them along the Z direction, and the Berry curvature can be computed like this. And now if you take this distance to 0, what you do is you annihilate the Chern numbers of the two monopoles, but so you annihilate the topology in a certain sense, but you keep an interesting quantum geometric structure in terms of the Berry curvature. So you keep this dipolar Berry curvature here emerging from this crossing point. And this crossing point, as well as the Berry curvature, are anisotropic, as you can see here, and they carry a memory of the merging direction. And the same you can do for these multifold nodes, which also gives you this kind of anisotropic Berry dipole. Now this brings me to multifold Hopf semimetals. Namely, we can ask the question, if we can have such a Berry dipole with a linear spectrum, which is isotropic, and doesn't have this quadratic branch stemming from the merging direction. So if you try to do this with a two-band system, so you take a vial-like cone, you try to put this kind of Berry dipole at the nodal point, you will see that it doesn't work. Because a fully linear Hamiltonian is written like this, where the sigma I are linear combinations of Pauli matrices, and this always gives you a monopole. So two linear crossing is always a monopole. What we can do, however, is to use multi-band systems. So if I take this 3x3 matrix here, where psi is something like a valley index, you will find that the energy spectrum of this Hamiltonian has this isotropic vial cone and a flat band, and the Berry curvature is not monopolar like for spin 1 to the spin 1 crossing, but now takes this point-like Berry dipole form, which is really located at this crossing point. So in a multi-band system, we can have a linear spectrum with this Berry dipole. And note that this Hamiltonian is not obtained from any merging, and this will be the main example for a continuum model for what I call a multifold Hopf semimetal. And we can already understand two words appear here: multifold because it's more than two bands, semimetal, well, it's a semimetal, and Hopf I will explain later on. So to analyze this more closely, this kind of Berry curvature has two important ingredients, which are the dipole axis and the dipole charges. Here I will always take the dipole axis along Z. So this is this axis here. And for example, for this threefold semimetal that I just showed you, if you compute the Berry curvature, you will find that these dipole charges here are given by -1, 2, and -1 for those three bands respectively. And you can, we have also models for fourfold and fivefold crossings, which always are linear and isotropic and have this kind of dipole form here with a certain distribution of dipole charges. And what is important now is that this dipole charge is distributed symmetrically with respect to zero energy, as you can see. And this obviously requires two bands, more than two bands, sorry, because in a two-band system, the Berry curvature of the conduction and valence bands are always opposite. So you cannot have this kind of behavior in a two-band system. Instead, we have this kind of sum rule in the valence or conduction band subsectors, which tells you that, for example, those two bands sum to 0, and here for a flat band, you have to take like half of the flat band for the upper and the lower sector. And notably, this attributes a strong quantum geometry to the flat band, which always kind of needs to compensate the charges of the conduction bands, because the sum of the Berry curvature of all bands still has to be 0. Now you can say, okay, funny continuum model. So what does this have to do with lattice? So let me give you some tight binding models that show this behavior. So I distinguish two classes. The first class has an even number of these Berry dipole crossings, which I will call a valley Hopf semimetal. And what you can do, for example, is take a 3D system consisting of these AB two-dimensional hexagonal layers, which are just graphene in this AB sector. And now you add a coupling in the AC, in the Z direction between A and C atoms, and with alternating hoppings, which gives you the sinus KZ. And if you go to the low energy limit of the system, you will find that at the K and K prime points, you have these threefold dipole crossings with opposite orientation, which are exactly described by this continuum Hamiltonian that I started with. Yes?
Sorry, for the picture of the graphene, why is there three different subatoms?
Oh yeah, I take layers A, B, and then I take an interstitial layer which just consists of these C atoms, which are not hexagonal layer, which are like which would be a trigonal lattice, right? And then I repeat in the third. Then I repeat the graphene layer. And I repeat this periodically in the Z direction. So I have 3 atoms per unit cell. That's why I have a 3-band system. And the second class of these Hopf semimetals has an odd number of those barydiapole crossings, which I call the true Hopf semimetal, because the barydiapoles cannot cancel in the sense that we will see. And those are a bit harder to realize in the tight binding model, but here's an example. So you could take a cubic lattice with 3 orbitals per side, and if you couple them in this way that is shown in this matrix, you will find that there's just a single of those threefold crossings at the gamma point. And it's again described by this continuum Hamiltonian that I showed before. Now the question is, okay, what is the physics of this kind of barydiapole? Why do we think they're interesting? So first simple thing to look at are Landau levels, which I want to compare for the Hopf semimetal and for a standard Weil semimetal. On the one hand for a single cone, and on the other hand for a pair of cones. So I apply a magnetic field, which can be tuned by this angle theta here from the dipole axis, away from the dipole axis. And what you will find rather easily is this spectrum for the Landau levels, where notably here you have this cosine theta term which appears, which is nothing else than the angle between the dipole axis and the applied magnetic field. So you can really, by rotating the magnetic field, tune these Landau levels from gap to gapless and maintain the flat band because the magnetic field does not destroy the chirosymmetry. And also note that this kappa alpha here explicitly appears, this kappa alpha of the Berg explicitly appears in the Landau level spectrum. And now to compare this to a Weil semimetal, for a Weil semimetal, it is well known that the Landau level spectrum for a single cone takes this form here. You have these 2 families of levels and a chiral Landau level, which is caused by the non-zero Chern number of the crossing point. And this Landau level spectrum is independent of theta because this cone here has a full rotation symmetry. In contrast, this single cone here does not have a full rotation symmetry because we have the specified dipole direction. And now another comparison that you can make is between this local dipole here and this extended dipole that you get from a pair of Weil cones. And you can see that, of course, for a pair of Weil cones, there's also a dependence on the angle between the magnetic field and the dipole direction, but the behavior is kind of distinct. So we always have this connected chiral modes originating from this, whereas for these Hopf semimetals, you don't have these chiral modes and you go from gap to gapless. A second thing that I want to show is the Anomalous Hall effect. Again, I want to compare these 2 systems. In the electric field, anomalous Hall conductivity is just given as the Fermi C integral of the Berry curvature. And you will find for both systems very similar expressions. So here we have E cross D, here is E cross D, but again, here it's an extended dipole, and here it's a singular dipole, which does not represent the distance in momentum space. What is, however, very different is the parity of these conductivities. So as a function of the Fermi level comes from this Fermi function when I go to 0 temperature. As a function of the Fermi level, the anomalous Hall conductivities of these systems have opposite parity. So for this kind of Weil semimetal, you get this symmetric behavior, whereas for the Hopf semimetal, you get this odd behavior. And this parity is exactly caused by this distribution of the dipole charges. I cannot show this here, but you can show that this even distribution, in contrast to this odd distribution, determines completely this parity of this anomalous Hall signal. And finally, a third response I want to look at is weak field magnetic conductivity. So we again start with this semimetal here. We apply weak electric and magnetic fields, and we do a standard semi-classical treatment with Boltzmann equation. And you can combine this with the semi-classical equations of motion, which are here corrected by by the orbital magnetic moment and the anomalous velocity caused by the Berry curvature. And you plug all of this into the current density, and this machinery gives you this important expression here, which is a current at linear order in the magnetic field, which explicitly makes appear these Berry dipole terms again. And again, this can be compared to this extended dipole from a pair of Weil nodes. And actually, all of these three expressions you can find in this current response of a pair of Weil nodes at linear order also. However, again, this D that I have here for the pair of Weil nodes is replaced by this extended Berry dipole. And they are called chiral anomaly, chiromagnetic effect, and magnetochiral effect, respectively. However, here we really have this topological monopoles, and here we don't have this kind of topology, but still we get the same form for these currents. And now, importantly, this has the same form, but again, it has opposite parity as compared to the pair of Weil nodes as a function of the Fermi energy, which you can show in a lattice calculation. This you don't see in this continuum model expression. Now, finally, let me show why I call these Hopf semimetals by relation to Hopf insulators. So to tell you about Hopf insulators, I would like to remind Chern insulators first. Chern insulators are just two-dimensional insulators without any symmetries. And the Chern number is given by the Biron-Zone integral of the Berry curvature. And this applies, for example, to the quantum Hall effect and gives rise to a so-called stable topology. In contrast, Hopf insulator is a three-dimensional insulator without any symmetry. So in your tenfold way table, you have a zero. So there's no stable topological invariant associated to these systems. But you can define a Hopf number as the third winding number of this unitary matrix that diagonalizes the Hamiltonian, just given by this integral. And well, to do this, you need to put certain constraints. You need to keep all the bands gapped. And this, there are certain constraints that refer to what's called delicate topology. And this is formally defined last year for this N-band Hopf insulator, but there are no concrete models known for more than two bands to study the physics. So what we find is that if we take our semimetals and we gap them, we find exactly these kinds of multi-band Hopf insulators. So we take, again, this semimetal with this one Berry dipole at the gamma point. We add an appropriate perturbation, which gives this insulating Hamiltonian here. And this actually represents the first lattice models for multi-band Hopf insulators. And they're rather simple because they only have nearest neighbor hoppings. There's only sines and cosines here. Whereas in the two-band Hopf insulators, you have very complicated second nearest neighbor hoppings. So to confirm that those are Hopf insulators, you can compute this Hopf number as a function of this tuning parameter here. And the flat regions are insulating regions, and the jumps are at semi-metallic points where this Hopf insulator has gap closings at some of these points here in the Biron-Zone. And at these gap closings, you exactly recover the Hopf semimetal that I discussed before. This is why I call it Hopf semimetal. So to conclude, I've shown you a class of semimetals, which we call multifold Hopf semimetals, which have linear band crossings with Berry dipole, as opposed to the linear crossings with Berry monopole that you have in standard topological semimetals. I've shown you that this dipole strongly affects physics. In some sense, it's similar to a pair of Weil bonds, which you could expect because there's this duality of the two dipole axes that appear. But it's also very different due to the symmetry of the kappa alpha of the dipole charges, which are distributed differently. And the name Hopf in these semimetals is due to the fact that they represent topological phase transitions between Hopf insulators. If you want to read more on this, you can go to this recent preprint. And as perspectives, I would like to mention experimental realization. We don't know about materials to probe these effects, but especially these valley Hopf semimetals with the graphene layers are very simple tight binding models, so there could be possibly something there. And you could probe these responses, for example, if you go with the Fermi level here to half filling, and then you vary the Fermi level, you will have this anti-symmetric response in the Anomalous Hall effect, for example, for this Hopf semimetal, and you will have a symmetric response in a Weil semimetal. And I would also like to mention 3 papers here on ultra-cold atoms, nitrogen vacancy centers and diamonds, and superconducting qubits, all of which have studied Hamiltonians very, very similar to ours. And this is just a proposal, but those two are experimental realizations. So I think with the method used in those papers, it should be possible also to realize some of these models that I showed you. And other perspectives include, well, the delicate topology of the systems that I haven't really talked about, and also generalizing these barodipole crossings to baromultiple crossings with octopole or quadrupole structure. And we already have some interesting results on that. So thanks for your attention.